Today we're introducing an important topic in electrochemistry, Voltaic or galvanic cells. These are devices that convert chemical energy into electrical energy using spontaneous redox reactions. We'll start with the simplest kind of galvanic cell, then build toward more advanced examples involving hydrogen electrodes, inert electrodes, and even systems where neither electrode participates directly in the reaction. These cells operate by separating the redox reaction into two half cells, allowing electrons to flow through an external circuit to perform useful work. The cell consists of two electrodes immersed in electrolyte solutions. The anode is the electrode where oxidation or loss of electrons occurs, making it negatively charged terminal. Another way of thinking is electrons are generated here. So a mnemonic would be like anox, anode oxidation, or LEO, lose electrons oxidized. The cathode is the electrode where reduction or the gain of electrons occurs, making it the positively charged terminal. A mnemonic could be red cat, reduction at the cathode, or GER, gain electrons reduced. These half cells are connected by a salt bridge or porous membrane to maintain ionic balance and complete the circuit, while an external wire allows electrons to flow from the anode to the cathode, generating an electric current. Ions must travel from the salt bridge to maintain a balance in charge. We will need to use a table of standard reduction potentials in aqueous solutions to determine which element will be either oxidized or reduced. To understand the table, it is oftentimes arranged from the highest reduction potential to the lowest. This means the cathode will be located above the anode because the cathode is where reduction is most likely to occur. Let's consider a copper-silver voltaic cell. First thing, let's look up the reduction potentials for both copper and silver. I see that copper is going to be a positive 0.34, and silver is a positive 0.80. Since silver is the larger of the two, then I know that it's going to be reduced. So we know that this electrode will be silver, and the other one will be copper. Okay, so we know that oxidation occurs on the copper now. So electrons will be leaving the copper, and they will be going over to the silver. So the silver is going to become negatively charged, and the copper is going to become positive charged. So we're going to say then that the copper will be the negative electrode and silver will be the positive electrode. Okay, each one of these electrodes are sitting in an electrolyte solution. So we'll say that we have a 1 molar solution of, let's say, copper nitrate here. And this side will be a 1 molar solution of silver nitrate. So as electrons are leaving the copper and going toward the silver, we will have Cu2 plus ions leaving, going into solution as S ions. And on the opposite side, we have silver ions accelerating or moving towards these electrons on the silver, causing silver to form, solid silver forming on the cathode, Likewise, the copper electrode will be getting smaller. Okay, in my salt bridge here, I'm going to have sodium nitrate. So, as the silver ions migrate to the silver electrode, it's becoming negatively charged. So I would expect then that sodium ions from the salt bridge will come in to help to neutralize that. Likewise, I would expect nitrate ions to come in to the beaker containing the copper electrode. If I were to write the reaction for each beaker, okay, on the copper side, I would have Cu solid forming Cu2 plus 2 electrons. On the silver beaker, I would have Ag positive plus an electron to yield Ag solid. Okay, for the voltage of this cell, we can see that E cell is equal to the E cell for the reduction minus the E cell for the oxidation. So on the reduction side was the silver, so that would be 0.80 minus the reduction side, which is 0.34. So if I subtract those, I would get 0.46. So my voltmeter should read 0.46 volts. Let's write the full equation. So I would have copper solid plus 2 silver ions to produce copper 2 plus ions plus 2 silver solid. Oftentimes you'll be asked to write line notation for these reactions. So to do that, we'll write copper solid, a single line, copper 2 plus. Okay, this will represent 1/2 reaction. Then we'll put a double line to show the other half reaction. So that will contain silver as an ion, a single line, and then silver as solid. To measure all reduction potentials, chemists need a universal reference electrode. That reference is the standard hydrogen electrode, assigned a potential of exactly 0.00 volts. The standard hydrogen electrode, or SHE, is fundamental in electrochemistry for determining standard electrode potentials. It operates under strict standard conditions, such as a platinum electrode immersed in a 1 molar acidic solution with hydrogen gas boiled at 1 atmosphere pressure and maintained at 298 Kelvin. In a galvanic cell, the SHE acts as a reference with a defined potential of 0.00 volts. When connected to another half cell, the measured cell voltage reflects the standard electrode potential of the other electrode. The standard hydrogen electrode can function as either an anode or a cathode, depending upon the relative potential of the other half cell. Hydrogen gas and hydrogen ions cannot conduct electrons directly. So an inert platinum electrode provides a surface for the electron transfer. When paired with copper, we will show the copper being reduced and hydrogen oxidized. Electrons will travel towards the copper and a positive standard reduction potential of 0.34 volts. It will act as the cathode, and a standard hydrogen electrode will be the anode when hydrogen is oxidized. So this side will be the cathode because a reduction is occurring. This side will be the anode because of oxidation. So for the half cell reactions, I can say here that copper 2 plus 2 electrons will produce copper solid. Likewise, on this side, we can say that hydrogen gas will produce 2 hydrogen ions plus 2 electrons. Our solution here would be something like copper 2 nitrate. I'll go 1 molar. And on this side, I will have a 1 molar H plus aqueous solution. So electrons will be traveling in this direction. So as this electrode becomes more and more negative, Cu2 plus ions will travel to the electrode and be deposited on the electrode. And if I have sodium nitrate in my salt bridge, if Cu2 pluses are leaving, I would have to have some Na pluses coming in to neutralize that. While on the other side, I would have to have some NO3 negatives entering into this half cell reaction. If you were asked to write a half cell reaction or line notation for this, okay, the line notation will be platinum, single line, H2, single line, H plus, double line, Cu2 plus, single line, Cu solid, when zinc is paired with the standard hydrogen electrode, zinc is oxidized and hydrogen ions will be reduced. The cell will have a negative potential of negative 0.76 volts. The standard hydrogen electrode becomes the cathode and electrons will travel to the hydrogen side and the hydrogen ions are reduced. So we know that this will be the anode where oxidation is occurring. The other side will be the cathode where reduction is occurring. The electrons will be traveling in the opposite direction this time. So we will call this the negative terminal. So here in this zinc electrode, it's going to be releasing zinc 2 plus ions. We know that negative ions from the salt bridge, So this example, nitrate ions will be entering. We know that on the other side, to equalize the charge, I would have to have Na plus ions coming in. Our half cell reactions will be 2H plus 2 electrons to produce H2, and zinc solid, zinc 2 plus 2 electrons. And my half cell reactions combined together to make a line notation will be zinc solid, single line, zinc 2 plus, double line, H plus, single line, H2, single line, PT solid for platinum. Not all galvanic cells use solid metals on both sides. Sometimes one half reaction involves a gas. Because chlorine gas and chlorine ions cannot act as an electrode, an inert platinum conductor is required. Platinum does not react, it simply transfers electrons. So to get started, let's look at our reduction potentials. So for nickel, I get off the chart -0, 0.24 volts. And for the chlorine, I see that it's 1.36 volts. Okay, so my inert electrode will be platinum, and my nickel will be my active electrode. Okay, so if I look at which one is going to be reduced, I notice that nickel has a much smaller value, so nickel will be the anode. And my platinum will be the cathode. So I know then that electrons will travel from the nickel to the platinum, which will cause nickel 2 plus ions to be leaving. Okay, my salt bridge here, if I'm using something like potassium nitrate, potassium ions will have to be entering, and I would have to have nitrates coming in on the opposite side to balance out the charge. Okay, so if I'm using nickel nitrate here, it has a pale green color, and this is clear on the other side. And if I use something like KCl, for example, on this side, it will become more green as the Ni2 plus ion concentration increases. So if I want to calculate the voltage Alright, so my standard cell potential will be, this will be 1.36 minus -0.24. So my voltage will be 1.6 volts. My half reactions will be nickel solid producing nickel 2 plus 2 electrons. On the other side, my chlorine gas will receive 2 electrons to become 2 chlorides. So my line notation for this one would be Ni solid, single line, Ni 2 plus, double line, Cl negative, single line, Cl2, single line, platinum. In the most advanced galvanic cells, neither half reaction contains a solid conducting substance. Both electrons are inert. They only exist to provide surfaces for electron transfer. This proves that galvanic cells do not require the electrodes themselves to react. They only require a pathway for electrons. In this example, we're using graphite, which is an allotrope of carbon. We're going to be doing a permanganate and an acidic solution. So we're going to have an acidic permanganate, which has a reduction potential of positive 1.51, and iodine will have a positive 0.54. So that means then that my anode here would have to be the iodine solution, which means then that my permanganate solution is on the other side. And it's going to be an acidic solution, so I'm going to put an H plus here. All right, so what's going on here is then electrons will be leaving, going in this direction. So electrons will be entering the graphite on the right side, which will be the cathode. Okay, my salt bridge, well, I'll go with potassium nitrate again, I guess. All right, so the two half cells. All right, so I would have to have 2 I negatives to produce I2 plus 2 electrons. Guess I should include an I negative here in solution. All right, on my permanganate side, okay, so this is going to be aqueous. All right, since it's an acidic solution, you require 8 pluses plus 5 electrons to produce Mn2 plus 4 waters. So it's going to be releasing some Mn2 pluses here, or producing Mn2 pluses on this side. All right, so if I was going to write my line equation, carbon, solid, single line, I negative, single line, I2, double line, H plus, comma, MnO4 negative, comma, Mn2 plus. Okay, I don't have enough room. Solid line, carbon solid like this. So I had to group all these together. If I wanted to calculate the voltage of this, so my E cell there would be 1.51 minus 0.54. So I would expect 0.97 volts from this cell. So to summarize, we can say that galvanic cells come in many forms: metal-metal ion cells, standard hydrogen electrodes, gas electrodes with inert conductors, fully inert redox systems, but they all obey the same fundamental rules. Oxidation occurs at the anode, reduction occurs at the cathode, electrons flow from anode to cathode.